Okay, everybody, welcome back. Happy Thursday. Today we are going to cover lessons 17 and 18. According to the calendar, we're supposed to just be finishing 17, but if you remember, we actually didn't start 17 last time. I made a game time decision and said 16 is enough for that one day. It was a tough day. So we're gonna do 17 and 18 here. We're gonna motor. I think it's reasonable to get both of these things done in an hour 40, but I'm gonna push it today. So be ready. So the topics for today, roots and radicals and rational exponents. You remember last time we talked all about radicals, square roots, cube roots, fourth roots, things like that. So we'll extend that and talk some more about exponents. And then we're going to do more work with radicals and then finally change gears into products of polynomials. And once we finish this working with radicals here and jump into the products of polynomials, it really is a completely different topic that we're moving into. You can see trinomials here and binomials there, and we're leaving exponents and radicals, but this is our last intense day of exponents and radicals, okay? All right, coming up, April the 11th is quest number 3. That's more than a week away, but not too early to start studying for it. For many folks, this is the toughest quest of the whole semester, because it's about radicals and exponents. Any questions on the calendar? Okay, so on page 137 at the top, in this lesson we examine the relationship between radicals and exponential notation. In the previous lesson we saw this example, cube root of x to the 21st. I actually think we didn't see that example last class, but we can just do it now. So we're going to do this one the way we did it last class, and then we're going to build a shortcut that we're going to use today. You recall that it would be so great to have what number up there in this problem? Love to have a 3. Love to have that power be a copy of the exponent, because then if it happens that we can get a magical 3 up here, then what does this entire thing simplify to? This is going to simplify to whatever is inside of the parentheses, right? The cube root and the cube will all cancel, and you will just get what's in the parentheses. So that is our goal. Put the right thing in the parentheses. But there's only one right thing to put in here. You have to still make the stuff inside equal to x to the 21st. So it is going to be x to some power. What happens to these powers? Add or multiply? Multiply. What's the magic number here so that you still have 21? Siete in English. 7. Okay, and as we said now, we've worked hard to make it so that the cube root and the cube are they're going to cancel each other. And so what's our final answer here? X to the 7, right? Just the stuff in the parentheses. Cube root and the cube all disappear, and you just get what's in the parentheses. Okay, so we built that a bunch of times last class. Hopefully you did homework and continued to build things like that. But hey, I'm ready for a shortcut, and I bet you are too. So let's look at it. What can you do with this 3 and this 21 to build the final power of 7? You can divide them. And isn't that exactly what we ended up doing, right? Where did this 7 come from? But thinking, okay, 21 times 21 is really what number times 3? Okay, that's a division, 21 divided by 3. Okay, so really the only way to get this wrong is to divide in the wrong order. Is it 3 over 21 or 21 over 3? To get 7, it's 21 over 3. Okay, so apparently the shortcut is that power divided by that index. That's our answer. So let's fill it in right here in this box. Nth root of x to the k. I know it's going to be a divide those two things, the n and the k. Just got to put them in the right order. Which one's on top? It's k, right? K divided by n. It says put lots of stars around this formula. We're going to be using this one a bunch. Okay, so for example, the 5th root of x to the 8 is really the same thing as x to the 8 divided by 5. Power on top, index on the bottom. I don't know if this will help you remember which one goes where. I don't think this mnemonic device that I came up with is all that great. So if you can think of one that's better, that works for you, share it with me and we'll share it with the group. We know that the 5 is called the index, right? We used that word the other day. Okay, so it says the index goes below deck. Below deck is like a ship metaphor, right? below deck, underneath. The index goes below deck, goes under in the bottom of the fraction. Okay, and then this one I'm really not sure about. Flowers grow up, yes? And powers go up. Power up. I was not feeling all that inspired, I guess, when I made this. I don't think it's great. I have not come up with anything better. I'd love to hear your opinions if you have a chance to think about it. Okay, let's take a look at number 3. It says rewrite the following in exponential form. Here we go. Negative 2y gets copied in parentheses. Give yourself a fraction line up there in the power. And carefully put the 11 and the 13 in the 2 spots in that fraction. Just got to put them in the right spots. What's on top? 13 over 11, right? It's really easy, but it's also really easy to put 11 over 13, and that's not right. Okay, this is going from a radical to an exponent. We could just as well go the other direction. So if I gave you x to the 2/7, I want you to start thinking, oh, hey, that came, because it is a fraction power, it came from a radical. So inside we are putting x. The 2, is it the index or is it the power? 2 is the power. 7 is the index or the power? It's the index. So x to the 2/7 is exactly the same as the 7th root of x squared. Good? Okay, so let's actually do some numerical calculations. Part A says 64 to the 1/2 power. When I first saw that, I said, oh, 32. I know how to do half of 64. That's not what 1/2 power means. Let's just take our time, recognize what it means. Fraction power always means radical. 64 is going inside here. We just have to put the 1 and the 2 in the right spots. Where does the 1 go? That's the power, 64 to the 1st. Where does the 2 go? Index, right up there. And we're actually not so used to seeing a 2 as the index. We just call that what kind of root? Square root, and we typically don't even write the 2. 64 to the 1st is just 64, so this is really saying what is the square root of 64? It is 8. Okay. And that's our answer. So 64 to the 1/2 is just 8. It might look strange the first time you see that 1/2 as a power. I'm not saying half of 64, we're saying the square root of 64. Also, with some practice, you start to make some shortcuts here. Half as a power always means square root. It always means exactly this. Let's take a look at part B. Again, fraction power says to me there's a radical floating around. In this case, negative 64 in parentheses. Where does the 1 go? It's on the 64. Where does the 2 go? Index. So this is saying, what is the square root of negative 64? What do folks think about that? It's not a real number. That's the right answer. The square root of negative 64 is not a real number. If that's not clear, just take a step back here. The reason 8 is the right answer to this square root of 64 is that 8 times 8 is 64, right? So that made 8 the right answer here. So there is a tempting, you know, like, well, maybe negative 8 is going to be the winner. But what happens when I multiply negative 8? It turns back into positive 64. And in fact, anytime you take a number and multiply it by itself, you're going to get something positive at the end of the day. And so there's no real number that will give me a negative 64. So we can just say not a real number. And that's our final answer at this point. Now, some of you have seen other numbers that are specifically, they're perfectly legitimate numbers, but they are not called real numbers. Anybody know what we're talking about here? Imaginary numbers, complex numbers. It's okay if you've never seen them. I suspect some of you have seen them before. We will talk about them later on this semester. We will introduce them. But as of right now, we don't have them. That is not a real number today. Okay, and then finally part C. Negative 64 to the half equals, I'm putting my radical there. Question is, what number is going inside? Is it negative 64 or is it 64? 64. That is 64. Remember, exponents are very weak. They do not reach as far as you might think. That 1/2 is only touching what? The 64. And it is not strong enough to reach that negative sign. which means there is a 64 there, and where is the negative sign? It's outside. Where does the 1 go? 1 is on the 64, 2 is the index. Is this one a real number, or is this not a real number? This is a real number, so in this case, the square root of 64 is just plain old 8, and that negative sign just gets copied down. Good? Okay, let's take a look at this next one. It's written out for us, 8 to the 2/3. Right? It's not a half power, it's a 2/3, but it still means radical. Where does the 2 go? On the power. Where does the 3 go? Is the index. And so you can see here, this is saying the cube root of 8 squared. So that's just the cube root of 64. And the cube root of 64 is just plain old 4. So that's fine. I'm going to give you another way to think about this one. I know that so far we've been saying that that 2, this 2 right here, goes on the power, right? It went right there on the 8. Let's just see what happens if we put it as a power outside of the radical. The 3 is still the index. It's still a cube root. Let's do the square at the end instead of at the beginning and see what happens. In this case, it's saying the cube root of 8 squared. What is the cube root of 8? 2. And how much is 2 squared? 4. And did we get the same answer as we did before? And the answer is yes. And this isn't just a fluke. It actually turns out all the time that when we say that that 2 is the power, you actually have complete freedom to either put that 2 inside the radical or outside the radical, and you will get the same answer. Word to the wise, if you are doing a numerical calculation, put the power on the outside. Put the power on the outside. Second way that we did it, but either way is okay. Okay, so to summarize, the most important fact for this lesson is right there. This is the thing that we wrote up above and you put stars around. This is the thing we just discovered, that you could put that k inside the radical like we've been doing most of today, or outside. You'll get the same thing either way. Okay, we're going to complicate things further by throwing a negative into the exponent, and dealing with that negative exponent is generally a good first step. The answer to this one is all written out. Let's ignore it. I think there's enough space for us to do this down here. So can you guys, in the blank space, just copy 16 to the negative 3/4, and we'll do this calculation. And try not to look at the answer written out there. Okay. I see a fraction exponent, 3/4. That says to me there's radicals lingering here. But before I deal with that, I'm going to deal with the negative part of that fraction. Anytime I see a negative exponent, it means move the thing, right? There's an invisible over 1 here. So if I move that 16 to the negative 3/4, where is it going? To the bottom. And when you move it downstairs, what does it change into? 16 to the positive 3/4, right? Okay, I can't have a fraction with a blank numerator. What number do I need to pull in here? It's got to be a 1. It kind of looks like the whole fraction flipped over. I don't think that's a good way to think of it. The only thing that moved was the 16. We just had to bring a 1 in to make this fraction complete. Okay, so equals 1 over. And now I've got 16 to the 3/4. That's a positive fraction exponent. That means there's a radical. Go ahead and put the radical. Before we even look at the power, what's the number in the radical? So that's a 16. And then put the 3 and the 4 in the spots that you know they go. 3 goes power. Now I'm going to write this in 2 spots. Can you tell me where we should put it? There or there. 4 goes where? Inside. Okay, this is technically not right. You can't have both. You can pick one or the other. They're both, so either one is okay. But here's the reason that I made the suggestion about putting it outside. Here's the deal. Does anybody happen to know what 16 to the 3rd power is? I mean, that's not one that's off the top of your head, right? So in order to do this, you either need to grab your calculator or maybe grab that chart on the front page, right? Actually, the perfect cubes are over here in green. 16 to the 3rd power is 4,096, but that is not one I have on the top of my tongue. But if instead of, and then even if we did it that way, now we are in the position of needing to find the 4th root of 4,096, which is also not one that I have memorized. So instead of dealing with that large number, 4,096, if we decide that we are going to put the cube out here. I'll put some parentheses just to really highlight the order of operations. Then this equals 1 over, okay, I'm going to copy my parentheses and copy my cube and just focus in the parentheses. What is the 4th root of 16? That's 2. That is one of the ones that I know. I don't know many 4th roots, but I know that one. And 1 over, what is 2 cubed? 2 times 2 times 2, 8. I know that one too. And that 4096 did not make any appearance in this problem, right? We would have gotten 1/8 if we had done it the other way. 1 over the 4th root of 4096. Any guesses right now for what the 4th root of 4096 is? It is 8. But again, that is not in my wheelhouse. So this is why if you're doing like numerical calculations, put that power outside the radical. Makes it so you don't have to deal with numbers as large. Okay, next page. Last example. We're going to put all of our exponent work together on this problem. So here it goes. It says simplified 35x to the negative a half over 20x to the third, all to the negative 2. Now, this problem probably could have been in a previous section. I put it here because there's a fraction exponent. But if you take a quick glance at the answers that we put up here, none of them involve radicals. So we're actually not even going to translate any, we're not going to translate that 1/2 power into a radical at any point. So this is really just using old properties of exponents. Okay, a couple of methods. We're going to just read this one and follow along. Let's take a look. Okay, first thing, 35 and 20, for sure we want to reduce that. What number goes into both? 5 goes into both. So 35 becomes 7 and 20 becomes 4. Okay, so in method number 1, you can see the very first step involves making a 7 and a 4. And also in method number 2, a 7 and a 4. Okay? All right. So let's take a look at method 1. One technique would be to recognize, hey, I've got a negative exponent in here, and that means I can move it. So where does that x to the negative 1/2 go? The bottom, and becomes x to the half, which is right down there, okay? What do we do with exponents when they look like this? We combine how? The two natural choices are add or multiply. Multiply those powers? Thea says. Oh, the powers? What do we do with those powers? I was thinking. Yeah, I mean we're multiplying x's here, but the shortcut we developed says you should add those powers up. And I mentioned before we started any of these exponent properties, like right before the test, the day before the test, it's so easy to pick the wrong property because there's a lot of natural things, like things that seem right, but you got to make sure you are applying the property, the correct property. So yeah, so we add those powers up. That is 3.5. I've left it here as an improper fraction. 7/2. Okay, we have gone as far as we possibly can on the inside of the parentheses, which means the next thing we need to deal with is this negative 2 sitting outside, right? We have just been diligently copying it up until now. Okay, so we have a property. This is the quote distributive property. It says that negative 2 comes in and hits every single one of those factors, right? And so all I've done is I have copied. I haven't really even done any shortcuts. 7 to the negative 2, 4 to the negative 2, x to the 7/2 in parentheses to the negative 2. Good? Okay, let us deal with this piece first. What do we do with the powers in this case? Add or multiply? This is the multiply property. That's the multiply property. A power to a power is when we multiply. Okay, so we multiply those two things. 7/2 times the negative 2. We can put it over 1. Cancel, cancel. Negative 7, okay? And so there's my x to the negative 7. 7 to the negative 2 was copied. 4 to the negative 2, lots of copying. Okay, and then last step here, I've just got lots of negative exponents. Remember, negative exponents mean move. So we're just going to move everything. Where does the 7 to the negative 2 go? Downstairs, becomes 7 to the positive 2. Where does the 4 to the negative 2 go? Up. Where does the x to the negative 7 go? Up. And now the exponents are all positive. And the last thing is to just change 4 squared to 16. 7 squared to 49. So there's our answer. 16x to the 7 over 49. And if you haven't picked this up already, you can see why these problems are hard. There's so many steps and so many opportunities to use a property that you think is right and seems legitimate, but actually doesn't work. In this case, there's a couple of different options for doing this problem. Let's take a little quicker look at method number 2 here. And you can see at the end, we're going to get the same answer, of course. So 35 and 20 both become 7 and 4. That's old. Everything else was copied here. Instead of combining these x's here, which is what we did in the first method, let's just do our pseudo-distributive property right now. -2 comes onto all the factors, okay? You can see all 4 factors in this step just with the -2 on the outside, all right? Okay, how do we handle these powers? Multiply, -1/2 times -2, that's +1. How do we handle these powers? Multiply those guys, that's a -6. And now any negative exponent we're going to move. So what happens to the 7 to the -2? Goes down. What happens to the x to the first? It stays exactly where it is. Don't move everything, only move the things with negative exponents. 4, right? X to the first does not contain the instruction that says move me. Yeah. Where does the 4 to the -2 go? Goes up. Where does the x to the -6 go? Up. And now all the exponents are positive. One last step to finish this one. 4 squared is 16. How do you deal with those powers? Add them. 1 and 6, that's my x to the 7. And then finally, 7 squared is 49. So personally, you know, like, I mean, I have a preference between these two. I'm not even going to tell you which one I prefer because it doesn't matter. I mean, you have like a small collection of rules, and as long as you apply the rules correctly with a definite like simplifying goal in mind, you'll get there. And so it's really just about thinking about the rules and applying them in a particular order that's going to get you somewhere good. Okay, and then there's this note here. I think I've said this before. The moral of the story is that a lot of algebra involves taking one small step towards the solution and copying everything else. Very common mistake that I think students make is to try to do like 2 or 3 steps in one shot. And I think that is a bad idea. I think that up here, I typed all this stuff out. Almost everything that I typed from one step to the next was literally copy and paste, except I would make one small change, right? This -2, copy, copy, copy until I'm ready to deal with it. The 7 and the 4, copy, 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 copy until finally it gets someplace that I can handle, right? Lots of copying. Okay, so that's this lesson. You're going to work through the activity, and at some point I'm going to call you back together, and we're going to jump to the next lesson.